Yeah, now the second part to our SINEWAVE signal generator for the inverter. There is pulse width modulation signal here coming out. This is produced by a carrier wave, which is a high frequency triangular wave, and two 180 out of phase sine wave signals, low frequency 50 Hz. Now I'm going to show you how this happens, how this is going to produce a pulse width modulation signal. But as usual, we read our script. Remember, all videos would actually be having this script reading. This is electronic waste benefit philosophy. Please remember, safety comes first. Safety is important. Electricity can kill. You need experience working with electricity. If you don't, please get someone who can show you how to work with electricity. We assume that you have prior electronics knowledge before you do these projects, and please, we expect that someone 10 years and older can do this projects. We are looking at grade 5 and above. This is not an electronics training video. It's a description of how these circuits function. How do you actually design these circuits and how do they function? You can adapt, you can correct them, you can modify them, improve them according to your purpose and needs. These circuits can be used for training, they can be used for learning, they can be used at home, they can be used in industry. Our philosophy is use as much electronic waste as possible. If you can get to 100%, the best. And the required resources, a computer of course, for drawing and producing schematics, and producing PC boards, the PCB designing, and you need power supplies, maybe you need electronic components, of course, you need PC builds, soldering iron, a solder wire, multimeter and electronic tools, and most of all is the oscilloscope. You can't do this project without an oscilloscope. This is very, very important. Oscilloscope is required. Then the software is mostly the PCB software, like Proteus. You can download the trial version for free, or you can actually download any other free software. If you have one already, the better. And this project will require your time, will require your patience, will require your passion and your dedication. Thank you. I hope you enjoy this project. Enjoy electronics. So where do we start? Okay, last time we ended up discussing about the triangular wave, that the value or the amplitude of the triangular wave. Make sure it is 6 volt peak to peak, which is the standard. But on our power supply, you have your 14 volts, so this will be 7 volts peak to peak. Sorry, 7 volts peak, and then 14 volts peak to peak. We feed into our comparator circuit together with our two sine wave signals, and this is how it happens. You compare. Let's take for example one side. You are actually comparing a carrier wave, which is a triangular wave. Remember, we are using the standard 6 volts peak. So you raise the triangular wave by 6 volts, which is half the supply. Here, if we are using our supply voltage U to be 14 volts, you raise it by 7 volts according to our circuit, but let's use 12 volts for simplicity's sake. So we raise it by 6 volts, meaning that from 0 to 6 volts is the half line. This is the half line. Now, because it is raised by 6 volts, it will peak at 12 volts. So it's 0 to 12 volt, back to 0 12 volt, back to 0, 12 volt, back to 0, 12 volt. And our sine wave is also raised by 12 volts. In our circuit, it's actually 14, remember? Okay, not to confuse between those two. The 12 volt is the standard volt, because if you are saying it's a 12 volt system, 12 volt supply, 12 volt, but our supply, we have made it to 14 volts. You can use 12 volt, it's okay, it still works, but you remember you want to switch MOSFETs with at least 10 volts. They are best working with 10 volts gate voltage. The best is 15 volts, and maximum 20 volts. Beyond 20, the MOSFET dies. So we are looking at those voltages. That's the design area. You rather switch with a higher voltage. It turns on, the MOSFET turns on fully from 10 volts upwards. Well, a bit lower, but you rather switch your MOSFET with at least 12 volt. So that's the electronics part, which we are not going to discuss much here, but anyway, okay. So we are comparing the carrier wave, which is here, the triangular wave, with this low frequency 50 Hz, which I have shown in red here. The triangular wave is in black. The yellow shaded parts will describe why I put yellow shaded parts there. The yellow shaded parts is actually the comparing area, the comparison area of the red and the black signals. The black signal, the triangular wave. The red signal, the low frequency 50 Hz sine wave. So what is happening is you have a low frequency sine wave like this one. The one side is going up whilst the other one is going down. So this is 180 degrees phase difference. So you have a sine wave generator conditioned and then split, one inverting, the other non-inverting. So let's suppose the red is the non-inverted signal, so it is coming like this as a sine wave, like that, and then the inverted one is 180 degrees out of phase, the green one, like that. So you have these two signals fed to a comparator circuit, but then these signals are actually raised by 12 volts. So this whole signal here goes up and center at 12 volts. This is 0 here. Remember, this is negative. As you can see, this is 0 volts. So you raise by 12 volts, which means this line here has been raised up to there. So it's now centered at 12 volt. So the only part that you are comparing is this bottom part here. The top part you are not comparing. It's out of range because the triangular lies within this range here, this white range here, the triangular wave from 0 here to 12 volt. That's where the triangular wave is lying. Remember, this whole sine wave area has been raised up to 12. So the triangle is lying within 0 to 12 volt, peak to peak. This one is now at center 12 volt and is actually peaking at it from 0 to 24, which is 28 in our case. 0 to 24. So you have this part only being compared, the bottom part. So you are checking this one, compare it. Next time you are comparing that one. Then the next time you are comparing the green one. The next time you are comparing the red one. So you end up having a switch between this signal and that signal, from green to red, green to red. So you have your 50 Hz signal, which is alternating. Right, let's go back. Okay, right, this is how it is done. Right, you have your low frequency sine wave and your high frequency triangular wave. remember in our circuit, the comparing circuit, the triangular wave is going to the non-inverting, the sine wave is going to the inverting. So we look at that comparator, for instance. That comparator and that comparator, the action is identical. So we look at one, right? So this is going to non-inverting, the triangle. The sine going to inverting. So what does it mean? As long as the triangle is higher than the sine wave, we have a high output. So that will be a pulse. Where the triangle is higher than the sine wave, the output is high. It's a pulse. When it is low, the triangle is lower than the sine wave, the output is low, which is 0 volts. Remember, this circuit is powered, is a single supply, positive 12 volt, in our case 14, and ground. So you are having a signal that is pulsing between output VCC and 0 volts. So our low is 0 volts. Our high will be 14 volts or 12 volts for our circuit. Right. So now these are 1, 2, 3, 4. I've given this to indicate a changing amplitude of the sine wave. Remember, our feedback will change the amplitude of our sine wave. When we change the amplitude of our sine wave, the pulse width is changed. Remember, when we change the amplitude of our sine wave, the pulse width is changed. How does it happen? We said our triangle is fed to the non-inverting, our sine is fed to the inverting. So as long as the triangle is higher than the sine wave, we have a high output. So when is it high? We look at the black line. The moment it crosses the red line, it means going up. It means you have a high output on the comparator. So we take one line of the red, which is the sine wave. Let's take this one, for example, this low amplitude line. So here, at that point here, that's when you have a high output, but it only occurs for a very short time, because it comes here and then later on, after a very short time, it's already lower. Goes higher for a very short time and lower. So it's a very small, tiny pulse. But here on the second part, it goes up for that period, from there to there. That's our pulse width. And then as we go, it goes from here to there. So you can see that the pulse width is actually growing. It's getting bigger. Here it's bigger. Here it's bigger. Here it's getting smaller. Here is the biggest. From here to there. Here it's getting now smaller. It's getting smaller. Very small. Almost like it's not there at all. So you have a pulse that is smaller, big, bigger, biggest. Then smaller, getting smaller, dying away. So you have a changing pulse width here, a changing pulse width. Same with this second signal. Suppose maybe that's a regulation now. Suppose our sine wave is cutting through here. It means here you have that pulse width, and then getting bigger pulse width, bigger pulse width here, and then biggest, and then getting smaller, smaller, and smaller. And you can see, let's see this one, the last one. It's a bit big, the bigger, very big, getting smaller, getting smaller, getting smaller, like that. So you are comparing the bottom part of the sine wave, and you have a changing pulse width. So what happens is, when the voltage signal of the output, which is the AC 230 volts, is getting higher, this signal must get lower to reduce the pulse width. When you reduce the pulse width, it means the voltage output gets lower, and voltage gets lower, this signal must get higher. So you reach an equilibrium where the voltage is now regulated. this is how what happens with our feedback. I think I've explained it as much as possible. That's how we get our pulse width modulated signal. This is what is happening on our comparator section here. That's all. Actually, that's all it is. Make sure, only what you have to make sure is our level of the triangular, the carrier wave is actually half the supply voltage, the amplitude, which you can adjust here. You can adjust that one easily here. Adjust the triangular wave output amplitude so that you have it peaking at 6 volts, 7 volts, or in our case. And then also here you adjust your sine wave here to peak at 1 volt or so that at the output of these two op amps you have a nice 12 volt peak to peak, 14 volts because of our power supply. That's all. And you have a nice pulse width modulated signal output. Don't mind about crossover problems, like when this one is high, the other one is high. That would not happen, because at the crossing point, normally here on the crossing point, you not have that. Here, when it is changing from another one is coming, the carrier will actually taken care of. You will not have a pulse within that region, the crossing point. Okay, now why do I have two signals? Okay, let me open what I want to actually highlight here. Okay, now as this is opening, we go on. Yeah, these things happen. Okay, all right. I think right, what I want to open was this one, the split wave signal. Okay, something funny happening with my laptop here. Okay, but anyway, okay, we continue. Okay, now it is opened. Okay, right. This at this point here, this is the most critical point for inverters. Here, the cross point. You do not want both MOSFETs of the same line of the bridge to be on, otherwise you have a short. So at this point here, the driver IC takes care of this, what is called the dead time period. This point, this crossing point here, is dead time. In any case, when it is actually switching, you realize that at that point here, the signal itself already has a dead point. But in any case, maybe there is an overshoot, but the IC will take care of it. That's why I recommend use a driver IC to take care of that. So that was why I had to make it a straight point. Right, now how do we get our feedback? Our feedback, simple. Use a transformer, bridge, basically a power supply output of the inverter, then the output will give out a signal, a voltage signal, which you must actually here put a dummy load, and you have your signal output here. If this transformer gives you 5 volts, it means your Zener diodes on the feedback must be around 5 volts, so that it's 5 volts at 230 volts. Here, the filter, this is the filter circuit. This is capacitor, these two inductors, and this capacitor are actually filter circuit. You can play around with filter circuits, research about it, go on the net and look for pre-made filters that would work on a 230 volts output. It's 1 Henry here, but I doubt it can't be 1 Henry. It's in millihenries. Not very big, but a sizable inductor. We'll actually do capacitors. Well, check which one will actually be okay with your application. Yeah, make sure maybe the inverter itself is drawing less than 1 amp from the battery supply. That's all. And if it's drawing more than that, try to change around the capacitors and check your signal. The signal of the inverter output using an oscilloscope, you can check them on the output of that transformer here. You get a nice, you can't put it here. I think normally some oscilloscope will not want that. You can't measure your output voltage on the 230 volts, because this is the 200 volt output. So measure here on the 5 volts or 6 volts or 7 volts or 10 volts or 12 volts or 15 volts output that you would have here on the output. That would actually work very well. So that's our feedback circuit. As simple as that. Here is your bridge driver, which you have to research on it and figure out how you can actually do the bridge power block. Now we go to supply. How do we get 14 volts and negative 14 volts from 24 volts? Use DC to DC converter. You can use various ICs or various methods to get that, but this is what I have used. The IC MC34063. This IC, you mostly find this IC in car charger for cell phones. You find this IC in car chargers for cell phones. It's the most common IC used for car chargers. The only part that is missing there in that charger is the transistor. This transistor, you have to take it from another board, or you can buy if you can't find a transistor. The inductor, normally the one that is inside the charger would work, but if you want, you can get a computer power supply and use that inductor, which is within the computer power supply. It's yeah, other components you can find around. You can adjust this R5 and R4 to get you the voltage that you would want. I would prefer that you use at least 12 volts up to 15 volts for your supply. And the negative, this is the negative DC to DC converter, will give you a negative output voltage. Remember, the ground is common for the negative and the positive, but this is a negative voltage supply from the same IC, same transistor. The only difference is, as you can see, is the arrangement of this diode, and that diode you can put on heatsink if you would want, but normally if you use a TO220 diode, you don't need a heatsink. The inductor, not very much big, but check the one that you can get from the computer power supply. I think adjust this R9 R10 to get your voltage that you want. So yeah, that's our power supply. Simple is that. You can use many methods. There are many methods of producing your positive and negative supply from 24 volts. So this is a split power supply now, 14 volts and negative 14 volts from 24 volts supply, 24 volt battery. So now, as simple as that. Now maybe I show you another method. Instead, remember, we are using the Xr2206 IC here, which is made by Xr. Get on the website of Xr, download the datasheet, and you get this. Create this signal generator for the triangle, or this one for the sine wave 50 Hz. But you can also create those signals from simple op-amp circuits. This is a phase shift oscillator, which will give you a sine wave, nice sine wave circuit, sine wave output. And these components are actually measured to give you a around 50 Hz. We can adjust the resistors here. These two, this resistor R14, R8, R9, and R17 to give you a nice signal output. And read about this. Is normally called the Buba oscillator, but it's a phase shift oscillator using op-amp. As you can see, these are just voltage follower op-amps, but main signal oscillator is here. And then tape out your sine wave output. And this one also is a triangle oscillator. This is an integrator. This is an integrator. You have a square wave oscillator here, and then you integrate it to get your sine wave, your triangle wave. So you integrate a square wave to get your triangle wave. And this frequency is determined, if I remember, by this capacitor and this resistor, if I remember very well. Yeah, should be that resistor, or is it this one? Okay, research about it. We can find out your triangle wave oscillator using op amps. So you get your triangle wave here, you get your sine wave here, and feed into here respectively. Sine wave here, triangle here. Yeah, well, one capacitor, of course. So you can do, there are many methods. Or you get I think it's ICL38, or is it 3803? Sorry, I remember. I don't remember, but there are other ICs that can give you these signals: the triangle and the sine wave. Right. So this is basically the sine wave signal generator for inverters. Pulse width modulator, modulated sine wave, pulse width modulated wave generators to create a driver for sine wave inverter systems. There are many methods of doing this, but I think this is simple and straightforward way of doing it using recycled material. So, right, as our 8th circuit, I thank you. I think so far this will be okay, and I would need feedback from anyone who would have done this circuit, and maybe we have success, and yeah, I learn a lot from doing it. And this is circuit number 8 is actually basically an analog circuit. There are digital methods of doing it using microcontrollers, the AVR or the PIC, but this one you do not need programming tools, you need programming skills. So for feedback, please taoremirimi@gmail.com. I thank you. Good day to you all.